The world's population and energy demands are increasing, and fossil fuels are running out. We need to find new, cleaner methods to supply our energy needs. There is a way to provide almost unlimited energy without polluting the environment. An energy source with fuel enough that it would be like living in a world with continents of coal and oceans of oil. At Culham Science Centre in the UK, researchers are copying the processes that power the sun and stars for a clean, green, abundant source of power. This is fusion. Today at Culham Science Centre, we're going to go through what happens in a plasma pulse. That is, what do we have to do with the machine to achieve fusion? Because although a typical plasma in jet lasts only about 30 seconds, the activities that go into producing that pulse last for several minutes. To maintain a large volume of high temperature plasma requires a lot of energy. Here we are right by the national grid, so we can draw energy straight down to power jet. In order to even out our demand on the grid, we draw the energy down slowly, and we store it on two large flywheels, 780 tons each, spinning at up to 225 revolutions per minute. During the pulse, the energy needed to create the magnetic fields to control the plasma comes from the flywheels, and they slow down. More energy comes from the grid to heat the plasma to high temperatures. As the flywheels approach the required speed, we begin countdown.
Colin, can we start the countdown, please?
This lasts for 2 minutes and 30 seconds, while the subsystems and protection systems are gradually brought into action.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1.
At 0 seconds, the pulse begins, but plasma is not created immediately. First, the capacitors on the ohmic heating system are charged, and then the central solenoid is energized to a current of 20 to 30,000 amps. If we regard the tokamak as a big transformer, then this central solenoid is the primary winding, and the plasma is the secondary winding. This means that with more than 1,000 turns in the primary winding and only 1 in the secondary, with a relatively small current in the central solenoid, we can generate a very large current in the plasma, millions of amps. This current then heats the plasma, in the same way as a domestic electric heater or a light bulb. Current going through a wire makes it hot. This is ohmic heating. While the central solenoid is charging, the current in the toroidal field coils is also increased. These coils create the magnetic bottle that contains the plasma. This is a video of a typical jet plasma. When all the power supplies are ready, a carefully measured quantity of fuel gas is introduced into the high vacuum of the torus. This is typically 5 milligrams of deuterium, the same weight as a postage stamp, but as the current and temperature rise, the plasma is made to expand to fill the whole torus. The plasma current in this pulse is increased to 2 million amps, and with additional heating from high energy beams, the temperature rises to about 55 million degrees. Jet regularly gets up to 100 million degrees. Magnetic fields are used to shape the plasma so that it only touches the walls in the region at the bottom of the torus, called the diverter. You can see the bright light emitted here as this diverter region becomes an intense interaction zone. The flickering of this light is caused by turbulence on the edge of the plasma, called elms. The roaring sound that can be heard on the video is the powerful water cooling circuits for the magnetic field coils and the plasma heating systems. This heat would be used to generate power and supply it back to the national grid continuously. The small greenish flashes of light at the top right-hand edge are the reciprocating probe taking measurements at the edge of the plasma. The flashes are accompanied by a hissing sound, which is the pneumatic action of the probe stabbing into the plasma. All the light that is visible in the video is from the cool edges of the plasma. The red coloration is characteristic of hydrogen, or in this case, heavy hydrogen, called deuterium. In the center, the temperature is so high that all the electrons are removed from the atoms. Visible light from plasma is emitted by electrons, changing their energy levels in an atom. And since none of the electrons are still attached to the atoms in the core region, there is no mechanism for visible light to be emitted here. After the experiment is complete, the plasma current is reduced in a controlled way, allowing the plasma to shrink and die away benignly. On jet, this process can be repeated every 15 to 20 minutes and is mainly limited by the cooling of the copper coils used to create the magnetic field. In future machines, these coils will be superconducting and able to maintain high-power plasmas almost continuously. Future power plants will harness the fusion energy and feed it back onto the grid for our consumption.